Hi everyone, welcome to ECO730. Now we are going to continue with our third last lesson, which is on autoregressive conditional heteroscedasticity, or better known as the ARC. So what are ARC models? Remember that all the models that we've been talking about previously are linear models, but there are also non-linear models, and these are models that are able to explain features that cannot be explained by time series models. Okay, so these features include some such as leptokurtosis, which is basically a situation whereby a financial asset return have distributions that are sort of more distributed within a certain area, whereby a graph might show a fat tails, or it might actually show excess bigness around the mean. These are also models that are able to explain features such as volatility clustering, and this one is usually it's as a result of what happens to prices. Remember that in most cases, when there's a change in price, it comes in bulk. It doesn't come evenly spread, and so for that reason, the impact of that such price changes also results in volatility clustering, where the effect is not evenly spaced over time. All right. And then thirdly, we also have the feature of leverage effect. And usually, we know that usually when there's a change in price, that change in price is not the same when there's a positive impact or positive change in price and when there's a negative change in price. Usually, when there's a fall in price, usually the impact is larger compared to when there's a price increase. So the reaction towards a price reduction, especially in financial instruments, is more impactful than compared to when the price has increased. The reason why I'm referring to price changes and financial instrument is because these type of models are mostly used in financial markets, also in financial economics, and also this is actually really part of financial econometrics. All right, so and therefore when we are talking about these models, we are then basically saying, remember, usually we would say y is a function of the error term linearly with all the other models, but with these models we are basically saying y is a function of the error term, and the two of them relates non-linearly, and so therefore that's why we are saying y is basically the current value, or the current value of the series, which is related non-linearly to the current and the past values of the error term. And we assume that this error term is also IID, which is independent identically distributed. Okay, so that is basically what we want to look at. Now, what we need to understand is that, of course, remember I mentioned about the word linear and non-linear. We can have a situation whereby a model can be linear in mean and linear in variance, like our usual model. But we can also have a model that is linear in mean but non-linear in variance, like the general GARCH model, which is general autoregressive conditional heteroscedasticity. But we can also have other models that is non-linear in mean but linear in variance, like the bicorrelation models. But we can also have other models that are both non-linear in mean and non-linear in variance, and we'll actually see later when we talk about the TGARC, which is basically the threshold general autoregressive conditional heteroscedasticity. All right, now we also have different types of volatility models. We have the first one, the historical volatility, which is just the same as the calculation of variance that we normally do, and the calculation of standard deviation that we normally the one that we know from statistics or from econometrics 2 and 3. So that is the historical volatility. We also have implied volatility. This is only possible, and again, let me make reference to financial instruments or financial assets. This is only possible if we know the price of that financial instrument, if we know the time to maturity, when will that financial instrument mature, if we know the risk-free rate of interest rate, and if we know the strike price and the current value of the underlying asset. So if we know these values, then we will be in the position to actually compute or calculate the implied volatility. Okay, so if we don't know them, then we won't be in a position to calculate the implied volatility. And we also have the exponential weighted moving average. This is another type of volatility, and usually this one is just a simple extension of the historical volatility measure. And usually what happens in the exponential part is basically where we allow the more recent observations to be or to have a stronger if impact on the forecast of volatility than the older data points. So for example, if we have U1, U2, U3, sorry, UT minus 1, UT minus 2, UT minus 3. So then we would say the more recent observations, which will be, for example, UT1, will have more impact compared to the UT minus 3. So the current period will be more impactful in the forecast of volatility than the older period. And then we also have autoregressive volatility models, and this is also another type of volatility model. Now, if we have to look at the ARC and GARCH processes, now remember that one of the classical linear regression model assumption is that the variance of the disturbance term is assumed to be constant. In other words, it's assumed to be homoscedastic. But we know that because of the time series or the nature of the time series variable or values that we work with, there's usually larger volatility, especially with financial time series. If you're talking about exchange rate, if you're talking about stock prices, if you're talking about you know um, um, all these financial time series variable, exchange rate, and all that. So usually sometimes you have a situation where you have a relatively volatile period followed by a relatively quiet period, or the so-called tranquility period of tranquility. So because of such changes, then we actually know that there is no way that the variance can be homoscedastic, or the variance of the error term cannot be homoscedastic. And so therefore that's where the usefulness of the ARC and the GARCH models come into effect. And so therefore the ARC, which basically refers to the autoregressive conditional heteroscedasticity, is basically models that are actually specifically used to forecast conditional variance, okay, or conditional volatility of a variable whose variance is not constant. So that is basically what it does. So, and we are basically saying now this variance is basically modeled as a function of past values of the dependent variable and independent variable. So usually this arc is basically a special case of a GARCH, which is a generalized autoregressive conditional heteroscedasticity, where we are basically saying there are no lagged forecast variance in a conditional variance equation. So basically what I want to show here is that under the ARC model, the autocorrelation in volatility is basically modeled by allowing conditional variance of the error term, okay, to depend on what? To depend on the immediate previous value of the squared error term. So we are basically saying the conditional variance of the error term is dependent on the immediate previous values of the squared error term. Okay, so this is the variance, this is the past error term. Okay, so what we have here is basically the autoregressive conditional heteroscedasticity of order 1. Okay, and so that's basically what it is. So now, even when we model, we would have the mean equation, which can be written as follow, and we can have now the variance equation. So what we have here is a variance equation. Okay, so your mean equation you can see as that, but in order for us to differentiate this equation. So what we do is we basically we change this sigma squared, which is represent the conditional variance. We basically change that to letter H so that it's more distinguishable. So what now we can then say is that, so instead of now, so that if we do that, then we can have this equation as follow, where now we are saying this error term has the mean 0 and a variance, And then we now say that variance is expressed as a function of the past values of the previous error term, and depending on how many or how far we go into the past. Okay, so the first one will be the mean equation here, this equation 8.14, and then the second equation is the variance equation. So this 8.14 is the same as 8.11, and 8.15 is the same as 8.12. It's just that we changed the letter so that we don't mix the two, because the literature, in most textbook, we use HT to differentiate between the mean and the variance equation. And then, so usually when you estimate the model, the ARC model, this is how it looks like. Okay, so this is how the output looks like. And usually what you do when you are estimating an ARC model, you are basically testing for the ARC effect. Usually the null hypothesis is that there is no problem of heteroscedasticity. In other words, they are homoscedastic, and then the alternative is that there is a problem. So if you reject the null hypothesis of no heteroscedasticity, then you are basically saying the alternative, which is stating that there is heteroscedasticity, will then become applicable. And the moment you reject the null hypothesis, it actually then means that you have to estimate that model using the ARC approach and not your usual ordinary least square. And so therefore, and how do we do that? We check the calculated chi-square value against the critical value. If this value is greater than the calculated value is greater than the critical value, we reject the null hypothesis, or alternatively, we simply look at the probability value. So for example, here, if we see that the probability value is 0.00, so since it's less than 0.05, which is the level of significance, we can then reject the null hypothesis of no heteroscedasticity. And so therefore, meaning in this instance, for example, there is heteroscedasticity, and so therefore there is a presence of arc effect. And so from that point of view, we then have to estimate an arc model. And I'll actually illustrate this in the um, demonstration of how to estimate the arc model. So this is basically the theoretical aspect of the arc model.